Great. I have my phone here so I could see the next slide, so I'm sorry if it looks like something else. Great. So, great. So I'm happy to be here. My name is Michael. I'm a TailorMed graduate, and today I'm in charge of technologies of a company named TailorMed. We analyze medical images and help radiologists perform their work better and faster. But today you're not going to see any of those things because they're horrible. It's something that's going to ruin your night. So we're only going to be talking about the technology we're using, which is deep learning. So just before I start, after I start, how many of you have hands-on experience in machine learning? Okay, not bad. Oh, I didn't know you have. So, great. So, basically, deep learning is part of machine learning. And for those of you who don't know what machine learning is, the idea is quite simple. You have a question, you want to teach a system or an algorithm to understand how to answer it. So, you have, for example, we have a question of we get a person's height and weight, and our question is, what are the chances for him to be sick in some disease, for example. And for a small amount of patients, of those people, we are willing to call them, bring them, make some blood tests, and really inform them and know for ourselves the answer. But for the rest of the world, we don't know the answer. We don't want to make those blood tests. We only want them to give us, for example, their height and weight, and we want to teach the system to understand whether, to predict whether they're going to be sick. So, for example, we're calling the patients to the lab, and we now know that the red ones are, they have the disease, and the blue squares, they don't have it. And we want the system to be able to create some kind of a model. And then when someone who we don't know if he has or doesn't have the disease, we want him to come and give us, we will measure his height and weight and figure out that, for example, this person is not sick, while this one, we will predict that he should come to the lab and give his blood test. Okay, that's the main idea. But of course, this is a very simplified model. The real thing is much more complex because there are not only two parameters, and the connections between the parameters are much more problematic, and it looks something like this. And unfortunately, in many cases it doesn't work. And for years, and from around the 70s, researchers have been trying develop something that would look more, that would learn more like the best learning machine on Earth, which is obviously the brain. And I will share some experience I had recently. I was walking down my street, and suddenly a chameleon was passing the road, real thing. And I pulled out my phone, but until I was ready, he was already in the bush. But I was still able to take this photo, which I'm very proud of. You can actually see his nails here. It's amazing. And the next day I met my 4-year-old niece, and I showed her this image, and apparently it was the first time she even heard this word chameleon, right? And so she looked at it, she stared at it for several minutes, and that was it. And about a month later, I was looking at my Facebook, and I saw this funny album of images of animals. This was the first image, and I was near her, and once I had this image on, she immediately, and yeah, you guessed it, she said, it's a chameleon, right? And she only saw one sample, and we were talking, for example, in our company, about tens of thousands of samples. She saw one chameleon, and she was able to tell that this is a chameleon. So this is the main idea, and this is what the researchers wanted to imitate. And this led them to design something, a model that is called neural networks. Actually, it's called artificial neural networks, as the real neural networks are here. And here you will have to bear with me for a few minutes because it's going to be mathematics, but the idea is that a neural network's basic element is a neuron, obviously, and the neuron gets an input, and it produces something that we can call a prediction. If it's the last neuron on the network, this is what we're getting. This is the answer to the question. And actually the prediction is nothing but applying a function. Neuron just applies a function on the input. It's called an activation function. There are several types of them. Here I put the basic and the most useful function, which is called value. And the idea is the input gets 8, it returns, the neuron gets 8, it returns 8. The neuron gets -4, it returns 0. Okay, negative goes to 0. So this is the idea, and I did miss some point that we have here a weight and a bias. And before the input gets to the neuron, it's multiplied by this weight and added this bias. And these are actually the parameters that are being learned in the system. So I will show you just an example to prove that, just to show you that you can build in such a way something that would be interesting. For example, it's not very interesting, but for example, if we see samples, we see something that every time we get 11, 15, 20, we get some positive prediction, and every time we get 2, 3, minus 1000, we get 0. So, for example, for this one, I would guess that after learning, the network will converge, and we will get a weight of 1 and a bias of -10, and you can check by yourself so that if the input is 5, for example, then we would send the neuron -5 and we would get 0. But if the input is 16, we will get 6, and that's, it makes sense. And obviously, and to show something more generalized, if we have 3 inputs, then we just sum them. It's very simple. We sum them, sum those multiplications, we give it to the neuron, and again it applies a value. So look at this example for instance, and say we have 3 inputs, height, weight, and I don't know, the length of the arm. Okay, can anyone guess? And the prediction is on the right. Okay, the first 3 inputs give something that is positive, while the third row of inputs gives something that is 0. Can anyone of you guess what might be the law behind these numbers? Okay, so I'll tell you what the law I thought of is. You add the first 2, you reduce the last one, and if it's more than 0, then you give some positive prediction, and else you give 0. And if the network is good enough, and trust me, it's good enough, it will converge to the right things, then it will converge to these weights, and you will get the right prediction. And here it's marked in a big blue circle because the output is also a neuron. Just a stupid definition, but it is what it is. And here I changed a bit the numbers, and I will tell you the secret. And again, why am I asking this? Because I only get the samples. I don't really know the law. Otherwise, of course, I don't need the machine learning and all this stuff. I would just write the law and finish with that. So I'm guessing here that I added the law that the first neuron should get an input which is bigger than the second neuron, and I will show you the long story. I will show them the long story and tell you that for this, for example, you would probably prefer to add another neuron to the network, etc. You can add as many neurons as you wish to get more and more complex models to get the best prediction you can get. And trust me, you can choose the weights so that they will do what we wanted here. And what is interesting is that if you add another layer here, then 2 things change. One, the name of the model is changed, and now it's a deep neural network. Completely different. And deep learning is actually, deep neural networks are the same, so we finally got to deep learning. And the second thing is that you apparently you get a very you can really produce a very complex model if you have several hidden layers, and hidden layers are what you have between the input and the output. And apparently it's really good. And I'm not going to show you, all the mathematics of how it's trained, but it's trained and it converges, and it's quite amazing. But I will show you some results soon. The first neural network I designed was about more than 10 years ago. The task was actually to classify vowels. Do any of you know what vowels are? Some of you probably know. It's A, E, I, O, U. Unless you are somewhere from Scandinavia and it's A, E, U. But forget about that. I just visited Finland. So the idea was to record people and to produce something that would be able to distinguish between those vowels. And of course I wanted the output to look something like this for A, but I guess that this is a perfect system. And I had quite a lot of data here. It was more than 10 years ago, but that was a lot of data. I had 20 individuals which were kind enough to record themselves for me 15 times, each vowel for 3 times, and I had 300 samples, and I also had some noise samples. And the network looked like something like that. Okay, it was 12 input neurons. Why 12? Because I put the 12 most powerful frequencies of the audio track. And why did I do that? I will get later to that, but I got a very good advice from my advisor then to do exactly this. And we had 18 neurons in the next level, which were all connected, and another 18. And finally, this classification model, which gave us the distribution. So if you can just, count roughly, you will get that there are more than 1,000 different parameters in this network, and it took about several hours then to train it. And the results were very nice, I believe so. So the high PQC is it's always the right answer. And for some of you which are not very impressed by around 80% accuracy, I have to say that at that time I had zero knowledge in audio, zero understanding of how the vocal system is built, and actually quite close to zero knowledge in neural networks. And while these results were very, very nice, there was something frustrating here, obviously, and it's the noise was a bit frustrating. Apparently noise sounds like E more than any other vowel. But more frustrating was the fact that while I had zero knowledge in audio, my advisor had some knowledge in audio, and his advice was a smart advice, which I really kept to myself, and I was sure it was like a secret. And about a year and a half later, when I got to this challenge of classifying digits, I would say it as an understatement, and I used the Fourier transform and the 2D and everything, and it failed completely. This was the 12 first coefficients were absolutely useless. And why anyway I had to do all this pre-processing before? Why did I need that advice? Well, the answer is that apparently data can be quite heavy, and no neural network can receive, for example, in my audio tracks, 44,000 elements, right? It's like, think about if it took me 2 hours to train the network with 1,000 parameters, this network would have, I guess, at least 40,000 parameters. So, yeah. And no network has 2 neurons in the hidden layer. It's quite much more. So it will take me forever. And I'm not talking about images, right? This is an image. No one can take today, I think, in his phone an image of 1 megapixel and multiply it by 3 RGB, and you get something that is absolutely impossible to give as an input for a neural network. And that's why people were very smart people were working for the last many decades on features. And that's exactly what my advisor told me to do, to extract a feature. What's a feature? Quite simple. You look at the image or at a certain area in the image, and you extract the data that you believe that would be smart to extract, so that the network will be trained on that data and not on the raw image. And there are many types of very smart features. For example, if you want to build a system that would be able to distinguish between oranges and apples, you would probably go for color, for example, something that will, I don't know, get the 5 most common colors in the image, okay, and that would be 50 numbers. But if you want to distinguish also between an orange and a pumpkin, you should probably go to something that is related to texture, because pumpkin would have those lines and orange is less, only in that small area. And more and more features, and all of this just to create that learning on exactly those things. And this tension was there for quite a lot of time, because on one hand, you couldn't give big inputs to the system. On the other hand, you didn't want someone to be working to extract a feature, because we had this amazing system which is the closest to artificial intelligence. No one has done anything as close as that, but you still needed a person, probably a smart person, to be able to define you those features, which were actually, it's not enough that they were hard to think of, they were very domain specific. Think of, I want to find leaves in my image, so leaves can be on a tree, but they can also fly, and can also be on the floor and even on the water. But if I want to find eyes, well, eyes usually are in someone's head, usually. So there were some very smart features. I don't know if any one of you is familiar with these features. It's a whole family of features which were very smart. It's hard-like features, and people written great papers which were really working. For example, to detect faces with these features, which, by the way, mean that you put the filter on the image and you sum everything that is under the white, and you subtract everything that is under the black. Right? And apparently it works great for object detection. But again, it's a human-crafted feature. And they tested it. The biggest test, and probably some of you heard about, is ImageNet. It's a huge database of images, but usually the challenges are on 1.2 million images, which are classified into 1,000 different classes. And so, and by the way, it's measured usually by something that is called top 5 error. You give the system the image, it brings you back 5 candidates, and if one of them at least is correct, then you're good. So it's, and I don't know how many of you can see, but the categories are crazy. Like, for example, for here, this is the container ship, but there's also lifeboat, an amphibian, a fireboat, drilling platform. 1,000 categories, so it's quite impressive. But the results weren't so good. Somewhere around 25% of the images, they couldn't even guess 1 of 5. So not bad, but not good enough. And why? Because when you have an image of a cat and it looks something like that, features can actually work. And I have quite a lot of experience in this from the last few years. They can work with such an image. But nothing can work with an image of a cat like this. Nothing that is based on features, because it doesn't look like anything that you're used to look at. So, and then came the convolutional neural networks. And the idea is, you don't want humans to be designing the features, but you do want to reduce the data. Well, let's let the network itself design the features, extract them, and train on them. All in one process, meaning that the features themselves are also trained. So, how is it done? I'm not going to get too too deep into this because it's mathematics, but the idea is basically that you build the feature as something that is a result of a convolution with a filter, and those filters are just matrices which you can train, and then it's just part of the process. These are features from the system, which was these features are the result of the training. And, you can all see that they are very much alike. Some of them are very much alike the features humans were able to design, but some and many of them and domain-specific features are very different. And that's the strength of the whole idea of convolutional neural networks. And there is, again, some catch. Well, convolutions are very compute intensive, and without these babies, no one would have been able to produce the results I'm going to show you. These are GPUs. And the computer on the right is very much like what we have in our company, for example, and it really helps to make the computation very fast, as GPUs just are very good in convolutions. So that's for the results. After 2011, most articles, most papers are using convolutional neural networks. And the results are much, much better, as you can see, and even some guy that I saw tried to measure the human accuracy, and it surpassed the human accuracy lately, last year, and surely it's going to be better because, you think of it, obviously it's a container ship. Actually, I'm not sure that many of you know what a container ship is, but for example, in the digits challenge, these are the digits that humans, they weren't very good at trying to understand what digits these are, and the automated system wasn't very good at them either, but apparently better than humans. And today you can actually say that we are doing real data-driven machine learning, which means we really look at the data. We don't use humans somewhere in between. For example, in our company, which deals with medical imaging, we have only 2 physicians working for us. Usually, these companies had, a battalion of physicians around them. So, and that's because we don't need people to be sitting and explaining things in the data to some feature engineer, which would build the features. Also today, the networks, I showed you 2 layers of two hidden layers, but for example, Microsoft, last year Microsoft published a paper with a network with 150 hidden layers. In my opinion, they just wanted to show the size of their infrastructure. But also, people are moving to bigger and bigger inputs. For example, ImageNet are images of about 0.5 megapixels. Our images are about 0.5 gigapixels, and I can say we're entering all the image at once because that would be absolutely impossible, but it's getting there. And the training sets, well, Google has a great training set because they don't need for example, to predict diseases, but and they're training on huge data sets. But for example, other companies have quite a lot of problems with that. And the main challenges are, for example, how do you, that is the only imaging, medical imaging that you will see, and there is nothing horrible here. So the question is, how do you insert such an input, crazy input into your system? And everyone they're working on it because for us it's interesting and because it's a city, but for someone else it's interesting because of videos, and someone else because of panorama images, etc. How do you train on less labeled data? For example, one of the key problems of this area is that with these huge neural networks, you get a lot of overfitting. What's overfitting in a word? For example, I want to train the system to be able to understand, to distinguish between elephants and fishes. So and I don't have a lot of data. There's nothing to do. I have 3 images of elephants and 3 images of fishes. So here are the images of fishes. So what's going to be the problem? The network is going to train great, and it will always distinguish between these images and these images. But the second it gets a swimming elephant, which is very common, of course, it will never understand that this is an elephant, since it learned very well to know that an elephant is something green on the bottom, right, and something in focus in the middle of the image. That's it. There is absolutely no reason for the network to understand that an elephant is this animal, as a human being would. And so this is a great problem, and for these type of classifications, you need tons and tons of data, and you never know when it's enough. And here we connect to Demi's lecture, as we're having very hard time with all the big data. Another thing you want is to use not only the images. You want to understand that this is an elephant, but you have other things. For example, Google has some textual information around the image. How convolutional networks are not very well at processing text, although there are some models for that. So how do you use text to understand that this is an elephant? And another very interesting thing is can you provide new outputs to the same inputs you had. For example, I can tell that this is a motorcycler, but I can also create a caption, and this is a real work, and they managed quite well. So I will conclude that it's an area, it's a very developing area. There were some great advances in the last, I would say, 2 years, but the challenges are still here, and it's a great area to be working in, frankly. And not all results are very good, but most of them are. So thank you, and I would love to have some questions. If not from all of you, then from my friends here. Yes.
What kind of technology are you using? Meaning you're running the processing over the GPUs. It's probably proprietary code that you wrote, or you're using some kind of deep learning framework, because there are many of these.
Great. We are using CUDA, and we are actually not optimizing it because it's mostly okay. And unfortunately, for now, our bottlenecks are not in the GPUs, but rather in everything else. As I told you, for example, making the system train on the right spots, and look at images as humans look at. For example, no human would think that the grass is the elephant, right? And so we're focusing on how to make the learning much more efficient, and get rid of 80% of the data and train the system only on the right things. So that's the main challenge.
And another question. He's not paying me. It's okay. And about the data filtering and the feature extraction, because I think most of the work is there. Because if things are not compute intensive, probably it will be there. So you actually sit and try to extract more and more features from the images itself, and then just filter the irrelevant measurements, let's say.
The answer is that we don't design any features. We let the system design all the features. But the interesting thing is that, as I showed you, many features. Yeah, the extraction is all going with the machine learning, but the interesting thing is that in many cases, you don't want to throw away everything that humanity has achieved. So we are using some of them as part of the system, letting the system fine-tune them and create the real optimize the human crafted features, which are, some of them are, they developed it for 10 years, they knew what they were doing, so it's, we're not throwing them. Anyone else? Oh.
You know software today that can generate the new output that you showed in the last one that describes the actual Is there a software that can generate?
Is there a software that can generate these captions?
Yeah.
There is actually something in the web that I think in Toronto, Toronto University, I think they published a neural network that generates captions. But there is no software, as far as I know, something that you can, for example, buy, because it will still produce you these. But it's going to be there. I'm sure that in 5 years from now, no one is going to be captioning images, and they will mostly be all right, because even today, if you look at the media, some of them it looks like no one looked at them after you wrote them. So I'm guessing that it won't be much worse than journalists do today.
If I get it straight, there is currently a race in the world about training systems on basic or more complex problems. But there is a date somewhere in the future where you don't need to train systems anymore. All the data will be widely available, right? So systems for training certain topics is something that will die in a certain day in the future, right? It will become irrelevant. Am I correct, or do I misunderstand?
Well, it's an interesting question whether machine learning is going to die because all the data will be available. But the thing is that actually data is, when you say data is available, unfortunately, you're right for what is called unsupervised learning. When you do unsupervised learning, you don't need the right answers. You're just trying your luck with the system, and in some cases it works. But for supervised learning, unfortunately, every domain it's not going to happen very soon that you will have the labels, as the labels are the hardest part. For example, take our case. We have scans. No one, someone diagnosed the scan, but no one delineated all the terrible problems there are in the scan. So someone has to do this, and no one wants to do this because it's a very, very boring task. So, for example, in the ImageNet, they were lucky because this task can be performed by, in crowdsourcing. So that's, it costs a cent, and that's okay. But in real, in special domains, it will cost a lot, and it will take a lot of time until databases will be enough so that, we get to this plateau where you don't really need anything and the systems are better. But sometime, I'm guessing that you're right, and we will be only working on making the system get better insights rather than working on, getting the data and labeling.
Sorry. You mentioned the CNN. Say a word about RNNs.
About RNNs, no problem. I can say a word. RNNs are mostly used for text, and it's something that has to be sequential. And the idea is that you don't only save the parameters, but you also save something that is called the state. And from this, you can process something that has more than one instance. For example, video is perfect for RNN because you have a sequence and you want to remember what happened in the frame before. But for example, in the elephants and the cars, it doesn't really matter what happened before, so it's not important. And specifically, it's very useful for text, as text is usually sequential, and words and letters, and that's perfect for that. And it creates, for example, this one is a combination of a CNN and then RNN. That's why you can produce a sentence which is so beautiful, and although it means sometimes nothing, or I would say it's wrong, but it still looks like a sentence. So that's the idea of RNNs.
Do you have a way to visualize or understand the features
I will need the guy from your right to reproduce the question.
can you visualize or understand the features of the network learns?
That's a fantastic question. Can you visualize the features or understand, I would say, the inner parts of the system that was trained? So the answer is that it's very hard. This is one of the problems of of this kind of a black box. That it's very hard to understand what it's actually doing, and there are quite a lot of works on that, and we are also working on that. Why not? Both because we want to understand why are we performing well, but also because we want to prove it to those who are using it, because it's not like an elephant or a cat. You have to say that there is something bad here, and you want to know why you made that decision. So yes, you look into the layers, you look at what neurons are excited by what kind of inputs. For example, you can think of this idea, so I'm giving different inputs and I'm looking at how the system reacts, and from this I'm understanding, but actually it's like it's much like reverse engineering the black box, and it's not too easy. It's a really interesting topic in research.
Once you deploy the system continues to learn itself, or it's
once we deploy the system, does the system do we continue training? The answer is that any of you that would build such a system would want to do it this way if you have the labels. For us, we pass FDA, which means that the system cannot be touched after it's trained, and we only update it from in cycles. For example, in half a year, we get all the data, we retrain the system, and then deploy it again. But for all of you, I would definitely recommend, if you have the labels, if you have the right answers, to continue training. Yes?
What would be a good sample for the number of samples and the number of features, size of depth of the network, and the size of each layer? Like, what is supposed to be the ratio for me to be in a good place?
Okay. What would be the reasonable number of samples? What would be a reasonable number of, I would call it filters? What would be the reasonable number of layers? Well, sorry, I don't have the answer, the exact answer for that, but we are estimating it in, with, yeah, exactly. At about, you will want to have 100 times more samples than a human would need to learn the same task. Something like that. Okay? Yeah, and but that's a good measurement, because then you're really getting the system to be better and closer to a human being. But for example, radiologists, which are our customers, are trained on less than 15,000 scans in their whole life, and it's scans of all the body, of all modalities, CT, MR, ultrasound, everything. So we are planning, if we're going to cover all the body, we're planning on 100 times more, which is a lot. Great. So, thank you very much.